Okay, and we can then get started. So, welcome to the Reproducible Computational Environment Using Containers course, where we're covering both Docker and Singularity. I'm going to talk about Docker today, and Jeremy is going to lead the session on Singularity tomorrow for people. So, without further ado, first of all, I'm going to share my screen so you can see the material. Give me a second to do that. So hopefully you can now see my terminal and also the course website there. I also put the links to the course website for today in the chat. We also have a shared Etherpad where we can share useful links and information. It's quite hard to read because of the colors there and the size of the font, but you can go to the link there and look at that. And as time goes on, we can add stuff of interest or of use there to people throughout the course as well. So a couple of things to start off with. One is what the course is the level of the course and what we're aiming to do. So this is very much an introductory course. So we're here for essentially we're assuming that people have little or no experience of containers whatsoever. So we're starting from that assumption, and that this is going to be essentially your first exposure to containers in any sort of real way. So we'll start building up from the ground very much up. Now, I'm aware that there may be some people who've played around with Docker or Singularity already on the course, and if you have, you may find that the first bits or the earlier bits are going over things that you know or already have experience with. But we will get on to other materials, and if anything is unclear, okay, I'll have a look at that, Mark. If anything's unclear, please ask questions in the chat, or put your hand up or anything like that. I'm happy to stop and ask questions. The idea of this session is to make it as useful as possible to the attendees. So if you want to know anything more, then please do just let me know, and put your hand up and feel free to ask questions as we go along. So before we start in the actual material, I just wanted to say a few things about how the course is going to work and what we all need to understand. The first and one of the most important things of the course is that we want to make this learning as good a learning experience for everybody involved, and that means that we all signed up to adhere to the ARCHER2 code of conduct. That includes instructors, and that includes for instructors and for people attending the course. And essentially, the core of the ARCHER2 code of conduct is that we all be kind to each other and be welcoming, exclusive, and respect each other's different circumstances and viewpoints. And we all work together to make this course as good and as friendly place as possible to be. If you believe the code of conduct has been violated, then there's a link here where you can complete the form. So, so in terms of the course itself, we're going to have rather than separate lectures and practical sessions with it. This course is taught following the carpentries methodology. It actually is now. It wasn't on previous runs. It is now part of the Carpentries Incubator, which is where courses go in Carpentries before they become official Carpentries courses, where the development happens. And what we typically do is we work through the material together. So we'll go through the material. I'll do some stuff on the terminal, and at various points there are exercises for you to complete, or I will check that everybody's keeping up. So please do let me know, if you're struggling, if it's going too fast for you and you're struggling to keep up. And usually, if we were teaching in person, that'd be quite easy to judge, because I'd use stickies in the traditional Carpentries way. I've been to a Carpentries course and I get a good idea of where we are around the room and where people are keeping up to. But it's a bit harder to do that online. So please, if you're struggling to keep up, please do just let me know, and we can change the pace. And as I said, please interrupt with any questions you have. And if I can't answer it right at that moment, we'll defer it and go away and look at the answer, and then we'll come back. We also make use of this Etherpad I've already mentioned, which is a shared collaborative document. There's a link on the course page, and I put the link in the chat earlier, though I'm aware people who joined after I put the link in the chat may not be able to see that. So we can always put it there again. We may use that for different purposes throughout the course. Finally, feedback is really important to us in terms of improving how we approach change both during the course and after the course is finished. So in terms of the course itself, during the course, I need your feedback to be able to get it at the right pace and to make it as useful as possible to you, and to ensure that you've understood the topics we've been covering, and if we need to go over and reinforce something that we've already done again, that's fine too. Please just let me know if anything wasn't clear and we need to look at it again. And finally, we also gather feedback after the course, which is really important to us to improve the course for future runs and to make sure it meets the requirements for people as well as possible going forward. So please feel free to provide any feedback, both positive and negative. It's all really useful for us to help us continue improving the training we're offering. So with all that said, let's actually get started on the material. In terms of timings, I should say as well, there are some timings in the course schedule here. You can see the proposed timings here. We may be a little bit flexible, particularly around when breaks happen, depending on how quickly we go through the material. I will try very hard. I'll try very hard to keep the lunch break where it is. So rather than make sure we get the material that's slated before lunch, finished before lunch, I'll try and just stop at 12 o'clock to allow people to get the full hour-and-a-half lunch break. I'm aware that, particularly with online teaching, getting a chance to have a bit of a longer break, an hour and a half, is really useful to sort of replenish our brains and, give us a chance to get some fresh air, have some lunch, take a break, and come back ready to approach the material again in the afternoon. So I'll stick to the lunch break, but the other breaks might move around slightly depending on how we go with the material. Okay. So let us get started with the first session. I see there's some confusion over where the link is in the email and the link to the course. And the right link has been posted earlier on. I can post it again just to reinforce. It shouldn't have the spurious character at the end of the link. Okay, so let us start with the introducing containers section. So this one, unfortunately, we start with the sort of the background material, which is mostly me talking a bit and you doing a bit of thinking, but there'll be more practical stuff as we move on through the course. And like I say, if anything's not clear, please stop and ask me either in the chat or by putting your hand up. So a couple of disclaimers first off. Docker's actually quite a complex piece of software. It's used in lots of different contexts and for lots of different purposes. And we are unlikely in this course to give you examples that suit all of your potential ideal use cases. But we're happy to talk about your particular use case, and then try and help you out and help you understand what containers might mean for that. But in general, one way I think about this course is we're not trying to teach you everything here, because that would be impossible when it's something as complex as Docker. But what we're trying to give you enough is give you enough grounding that you can then go and explore the tool yourself, use additional online resources, because there's lots out there around Docker and containers, and it should give you the confidence and the understanding enough to be able to explore those resources and explore it a bit more yourself with some more confidence and understanding of what the terminology is. So giving you a boost to start that journey around using containers. And also, containers are a topic that requires sticking out a technical background. So we're going to talk about containers and the technology behind them and how they work in quite a hand-wavy sort of way. right? There are lots. If you go and look at how containers actually work, they can work in quite different ways depending on the container technology, and it can get very technical very quickly. So in some cases, our analogies may not match exactly what's happening technically under the hood with containers, but sometimes when things go wrong, it can be quite hard to understand what the diagnostic error messages mean, because they don't really tally closely unless you have a very clear technical understanding of how containers work. In most cases, that doesn't matter, and actually, since the advent of sites like Stack Overflow, it's usually easier than you think to get past a really horrible looking error message, because you can put it into Google, go to Stack Overflow, read the description of it, and actually pretty quickly find a workaround of the way to go. But just to be clear, this course will not provide you with a deep technical understanding of how the containers work. Hopefully, it'll give you enough of a feeling for what containers are and how they work, and then enough practical skills that you can start exploring them in your work and research. Okay, so that's just to set some expectation levels. So, there's a challenge here about what your experience is. Taking a minute to think about the challenge you've experienced using scientific software or software in general in your research. And you may recognize some of the following sorts of issues that people hit up against. So you want to use a piece of software that doesn't really exist for the operating system that you'd prefer, be that a Mac, a Windows system, or Linux, depending on what you're using. You may struggle to install a software tool because there's a huge number of dependencies first, and these dependencies have their own dependencies, and so on and so on and so forth, and you end up with this horrible mess of complicated stuff you have to install before you can even start doing any useful work, and you spend so much time stuck even solving a problem of installing something you didn't even think you were going to have to install in the first place, because it's a dependency of the thing you actually want to use. And you can also get this problem with this sort of combinatoric problem. The software has many dependencies, and only a subset of the versions work together properly. So you end up with this thing where you try and version 3 of one piece of software against version 2, and it doesn't quite work, and you have to fiddle about with the versions and end up into this horrible thing. And again, you're doing lots of work that you don't really want to be doing, because your job is usually, I want to get on with my research and do the thing I'm interested in, not hack about trying to get the right combination of things installed so things work. The problem is that you tend to do this on the fly. You start off with good intentions, but there's so much fiddling about that you get to the end of it and you don't really actually know what you ended up installing, but you don't want to touch it again because it might stop working. So you're not actually sure what version of different bits of software you're using, because the install process was so ad hoc and circuitous, and you had to make lots of other decisions on the fly and try lots of different things. You may see sometimes yourself and a colleague get the same software but get different results, because you've either installed different versions or using different operating systems, or something's different, but you don't quite, because it's something so complicated, it's very difficult to track down what could be different and lead to the different results. You got it all working, but your colleague says, "Oh well, I'd like to do that as well. What was your experience?" And you give them your install instructions, but it doesn't quite work on their system, and you don't understand why. And again, you're back into the same problem of having to fiddle about with the bits of software rather than actually get on with the work. You may have written a package for other people to use, but a lot of people really struggle to get it working and struggle with the installation, and it's stopping take up of the tool you've designed and made available for people that could have a really big impact on their work, but it's very difficult to get working. And finally, you need to reduce a research project from a former colleague, or actually commonly here is also the former colleague could be your past self 2 or 3 years ago, or even 1 year ago, and the software you used was on a system you don't have access to. It's a laptop that broke, or you got a new laptop, you don't have the piece of software anymore, and you don't quite understand how to get back to that state so you can reproduce the results, either because of a query on a paper or thesis or something like that, as well as other reasons. So there's lots of problems, right? All these characteristics really boil down to the one sort of typical fact, is that the main thing, the tool you want to use or the tools you want to use depend on many other bits of software, including the operating system itself. And it can create a very complex, often very fragile system. One change or missing piece can stop the whole thing from working and break something that was already running. And it becomes complex to actually get back to where you were previously, or for somebody else to try and reproduce what you're doing. And this situation is often referred to as dependency hell, and you may have heard that term. Particularly, it's a term that arose into common use, particularly around installing Python packages and getting Python packages to work together. Say you've got something like Conda, and you've got competing dependencies from two different bits of software. So, and it's there's another thing here about about thinking about what these challenges actually mean for doing research. It says software and science here, but obviously, research isn't exclusively science. But there are real negative consequences for research, and you may have actually experienced some of these yourself in real life. You can't use a specific tool at all because it just doesn't. You just couldn't get it to work. You thought it was a really good idea, may have led to something really interesting, but you just couldn't get it working, so you had to abandon that route. You can't reproduce your results because you're not sure what tools you're actually using, and it's particularly a problem with a gap of time, from when you actually did the work, where it's all in your head, and further down the line where you find that actually you wrote a lot of things down, but you can't quite get to the being able to reproduce your results. There's something missing. You can't use different resources. Say you get access to some cloud credits or something like that, and you want to use, suddenly scale up and do everything in AWS or Azure or whatever. You're not able to replicate your software setup, and you just can't get it to work at a bigger scale or on different resources. And again, we're back to the thing of other people can't validate because they can't recreate what you actually did in a useful way. So I've talked about all these things. Now, hopefully some of these things are familiar to you and you've come across them at least, or appreciate, that if you haven't come across them, that these problems do exist and out there. And there are various solutions to this. Containers aren't the only one. Like I've already mentioned, Conda for Python is one way to try and get around this. But okay, for example, it comes with its own problems. You can write documentation. There's lots of different ways to get around these. But one popular way at the moment, and the focus of this course, is containers. And containers provide actually quite a convenient way to package up software dependencies and all the resources they require, and potentially other things that are required to capture the environment you did the research in or did the work in, and put them in a way that can be reused by other people or by yourself in the future. And I also, to a large degree, portably across lots of different systems, so you don't have to worry about just having access to the same type of system, the same software setup underneath. But how do they do this? We've mentioned containers, I mentioned Docker already. What actually are these things? So a container is a generic thing. Docker is a tool that allows you to build containers. It's not the only one, but it's the one we've chosen for this workshop, but it's very, very popular is one of the reasons we've chosen Docker, and quite readily available for lots of different platforms. But what actually is the container itself? Well, maybe to understand that, you need to understand a bit, hopefully, about what a computer is. But it's probably a lot of people understand this, right? But you need to understand particularly what's the hardware. There's different parts of a computer, such as the CPU or the processor. There's memory or RAM that your computer uses temporarily while it's switched on, while it's running programs, or the hard drive or storage, which stores information long term. All these pieces come together and actually constitute your computer. We don't see them really because they're hidden from view. Instead, what we see is the software that sits on top, which is all the programs, the different files, the ways to access them through the software that's known as the operating system. And all of these things are essentially a file system. Okay, so everything on your computer, be it programs, be it pictures, be it documents, the operating system itself, everything lives on the file system. in some way. Now, if you want to install some new software, don't take the mess up what you already have. Then you don't want to buy a whole new computer, though that's one approach to do it. It seems a bit expensive and a bit of a waste of resources. The idea is that you could have an independent file system and running an operating system insulated from the stuff that's mainly installed on your main computer, but provides the same sort of functionality in a sort of independent way. So a container is a way of doing this. It's a way of providing an alternative, essentially, file system, which is separated logically from the sort of standard file system of your computer, and can't affect it and can't muck it up. So, imagine you've got two tools you want to use to do your groundbreaking research on cat memes, right? There's one called Perling. It does amazingly well predicting the best text for a meme based on the cat species, and WhiskerSpot, which is the only real tool out there that's used for identifying cat species for images. You want to send these cat pictures to WhiskerSpot and then send the species output to Perling. But there's a problem here, right? Perling only works on Ubuntu, and WhiskerSpot's only supposed to for OpenSUSE, so you can't have them on the same system. Okay, this is obviously a bit of a contrived example, but what we really want is to have both of those things being able to exist on our computer at the same time, but without causing problems for each other, and build them together into a pipeline. And container systems allow you to do this. The container is essentially thought of as shipping container. It comes from shipping containers, right? Because before shipping containers, packing and unpacking cargo ships was time-consuming and error-prone, because different clients' goods got mixed up because they were all put in the hold together. You had to pick them out, check what that one was, put it in the right place, make sure it went to the right location. And instead of that, containers just keep things together that should stay together, and you just ship that standard unit of thing around, and it makes it much easier to deal with sending things and keeping things isolated from each other. So just like those shipping containers keep things together, that should stay together, software containers standardize the description and creation of a complete software system, a complete file system, actually, because all of this software is really just files. You should be able to drop a container onto any computer with the container software installed. That's the host system, and it should just work. Right? That is the sort of idealized view of how these sort of things work. Of course, it's not always as simple as that, and containers aren't a perfect solution, but they do provide a very convenient way generally of working with things with less problems often than other approaches. And containers are really just an example of, you may have heard of virtualization and virtual machines accessible from a host computer. It makes it essentially, think of it as having a virtual computer running and accessible from the host computer. So before containers, there were things called virtual machines, VMs. They were very popular. They've been very popular in cloud computing and were integral to the startup of things like AWS and Azure and Google Compute Cloud and things like that. A virtual machine typically contains a whole copy of the operating system as well as its own file system, and gets booted in the same way as a computer would. Containers are a bit more lightweight than that. Underneath, the container usually uses the Linux kernel that's running on the host machine, and simply has a different layer of Linux and the file system on top of that, which means that they don't need to go through a boot cycle every time they start up, which speeds things up, and they're much more lightweight in terms of memory use and ability to start up and shut down. They're much quicker and easier to use. They tend also to be a bit smaller in terms of sharing them with people, because a VM has to contain a lot more data. This has its downside, in that containers are essentially Linux only. Okay, so you can't certainly, though that I don't want to say can't and never and those sort of things, but at the moment you can't really. It's not very common, or you can't really create, for example, a Windows container which runs Windows OS. Now, I'm sure there's work out there to make such things possible, but they're not generally seen. The same for Mac OS, because neither of those things really are Linux, and you need the Linux operators. So when you're running things, the Docker thing on the Docker desktop on Mac or on Windows, what it actually is doing is providing a Linux kernel, Linux environment that then can support the containers. So just want to clarify some terms. The container is the alternative file system you can access and run from your computer. You also come across the term of the container image. That's the recipe or the template for running a container. It has all the information required to start a running copy of the container. And you know, the running container itself tends to be transient is started up and shut down. The image is more long-lived. It's the source file for the container. It's the thing that says this is how you make the container work. So one way, as it says here, to think about it is the image, the container images or image. It's often shortened to the container image. Is like a cookie cutter or a biscuit cutter. You know, it creates multiple copies of the same shape container. So the image generally on-chain, it does not change, but the actual cookies themselves come and go. If you want a different type of container or biscuit or cookie, if you're more American, then you need a different image to produce it. Okay. So why is this helpful to us, right? Because I started out talking about all the problems around particularly scientific software and using scientific tools. So the many different layers make it really hard to install and reinstall scientific software, which hinders the reliability and reproducibility. Where the container is a self-contained, complete, separate computer file system, then it has lots of advantages and solve or potentially solve some of these issues, right? So it solves quite a lot of the problems. Documentation, there's a clear record of what software and software dependencies were used from bottom to top. You'll see that later when we talk about how you define a new container. You'll see that what it actually comes down to is a record of exactly what was installed and what it looks like. It potentially solves portability issues. The container can then, once you've built a container image, it can then be taken to any computer that has Docker installed on it. Doesn't matter whether that computer's a Mac, like mine, Windows, which some people here I'm sure will be using, or even Linux, which some people here will be using, and which we will definitely be using tomorrow when we look at Singularity. Reproducibility. You can use the exact same software and environment on your computer and on other resources. So, for example, tomorrow we'll see on the HPC system, ARCHER2, but also like scaling out into the cloud or getting access to a central large system at your own institution. And configurability, so containers can be sized to take advantage of more resources, for example, memory, CPU on larger systems, or less depending on the circumstances. So the same container can be used in lots of different ways and can take advantage of the different resources. So what we're going to do for the rest of this workshop is show you how to download and run pre-existing containers, things that people have already built. These are images that are already out there. And then how to create and share your own containers. So that's in Docker anyway for day one. And day two tomorrow we'll have a closer look at Singularity, which is a different container technology that's more suited to running on remote HPC systems. So we've chatted. Well, chat, that's the wrong word. I've talked at you a bit about containers. What they do, what the issues we're trying to address, particularly in a research and a research software context here, which is what we're primarily interested in. So you can probably think of some other use cases in your area of work, but some common examples for getting use cases in a research context, include things like just using containers solely on your own system, to use a specific software tool or to test out a tool, and just totally avoid a complex installation process and save your time and avoid dependency hell. This is one of the biggest uses I have for containers. We can think about it in terms of the more complex stuff about reproducibility and pipelines and things like that. But actually, just being able to avoid having to install tools that end up being a complex thing saves me so much time. We'll see an example later on of using a tool called Jekyll, which is used to build websites, including carpentry websites, such as this one. Now, getting Jekyll installed is a real pain in the neck. It's a horrible piece of software to install because of all the dependencies it has and things like Ruby and other stuff like that. But there is, as you'll see, there's a container image publicly available on Docker Hub that provides an official recent Jekyll, and you can just short circuit that whole installation process and just use the Docker container instead. And the number of hours of my life saved by just using Docker containers were I would have had to worry otherwise about getting something working on my system, and searching out on Google for how to solve this problem. It can't be underestimated. It's a really big use case. But also, in a more researchy way, I guess it allows you to set up the software in the container and then share it with your collaborators for use on their systems or on remote computing resources. And finally, archiving the container so you can repeat the analysis model using exactly the same software and configuration in the future to try and capture your workflow. And it helps you, your future self, go back where you often need to do and reproduce results that you thought you'd finished off with years ago. So yeah, at the end of each of these sections, we'll have a number of key points to it, and there's a lot in this one, in this particular section. But the key points here are almost all software depends on all the software components to function, but these components have independent evolutionary paths which can lead to difficulties. So small environments containing only the software that's needed for a given task are easier to replicate and maintain. That's the whole idea behind containers, is you have these little blocks of stuff together. Vinay, I'll come to your question in a minute. Just let me finish this little bit, and I'll talk about your question. So small, critical systems cannot be upgraded. May need to be reduced on newer systems and maintainable, safe, documented way. The common example of this is your laptop broke. You get a new laptop. You want to get back to where you were. Containers can help you do that quite much more quickly and easily than you would be able to otherwise. It's efficient because it allows you to run lots of different environments on the same computer without and installing this new thing, mucking up the things that are already working for you. It isolates them and protects them. This next point I'm not as convinced by. I have to say that improves upon the virtualization of whole computer. I guess this is saying why use containers over VMs. They're a bit more efficient than VMs because they use less resources. Okay, they're also a bit quicker and lighter weight. The actual big win over VMs really actually is they start up and shut down so quickly, and they're not as clunky to get going. Containers are built from recipes that define what's there, so you've always got some sort of record of what were the instructions were to build them. And although we're talking about Docker today, there are various other container platforms. Docker is not the only one. It is probably the most famous and the most widely used, and it does also have a cool picture of a whale associated with it, which is always a good point too. So Vinay asked in the chat, can we access commercial software from the containers? And the short answer is yes. I mean, like if you have a license for commercial software, then you could build your own container with that software in, as long as it was able to link to the license server that it needed, or you'd have been able to download the copy of the software. Also, some commercial software is out there and available in containers and may be distributed. Now, generally, you will be able to download it for free. Like many of the tools we're going to talk about, it may be controlled by the organization that provides the commercial software. But I mean, it depends what commercial software. It does depend a bit what you mean by commercial software here, right? So some commercial software is commercial but freely available, and some you have to pay for. But in general, yes, there's nothing different between commercial software and normal software, just that you have to pay for it, and the access to it's controlled in a different way from open source software. So there's nothing technically about containers that stops you using commercial software, but you do have to have access to it to make that work, and you need to be careful about how you distribute it, I guess. So let's have a quick go at starting to use Docker itself. Hopefully, you've managed to get Docker installed on your local system, so you can follow along here. If you haven't managed to get Docker installed yet, then please do say, and one of the helpers can come do say in the chat, and then one of the helpers can come and have a word with you and see where you're stuck and try and help you install it. But like I say, this will all be recorded. The material is not going anywhere. The material websites stay up for posterity as long as GitHub Pages is there. So you can always go back and run over it yourself if you've not quite got to the stage of having Docker installed on your system yet, and try it out yourself. So hopefully you've got Docker running. I can see that Docker is running on my system because you will be able to see, because it's a tiny icon. But up here I have a little icon which shows me the Docker desktop is running. It's a stylized whale with the containers on its back. And so for that's on a Mac. On a Windows system, it'll also show up in the sys tray somewhere to show you that it's running. Docker application often also provides a way for you to log into Docker Hub, which is a standard place for storing and downloading images online. Later on, we'll be looking at the Docker Hub in more detail, and you'll need to log in. But right now, for the first bits, you don't necessarily need to be logged in. I am logged in. My little sys tray icon here shows me my username, which is linked to Docker Hub, there, which shows I am logged in. But just be aware that when we come to the Docker Hub stuff, you may need to log in through the Docker desktop if it's running on your system. If you can't remember your Docker Hub username because you've been logged into the Docker Hub using your email address, you can find out what it is through the steps here. So if you're not sure what your Docker Hub username is, then you can always get back to them this way. Okay, but once Docker's running, we can open a shell. Hopefully, I've got a terminal window here on my Mac. Terminal on Linux should work just as well, and for Windows, probably PowerShell is likely the way to go. Or if you're used to using, for example, the Linux subsystems on Windows, they should work as well. So assuming Docker's running, you should be able to take Docker -- version and get some useful information, or not useful, but get some information back that shows you that Docker's actually working. So you see mine, it gets some sort of version number, a build number. I think that's the most recent version of Docker, or the most recent release of Docker that's out there. That's on my system. So we've not actually done anything really on Docker to run containers here. All we've done is we've checked that it's installed and we can access it correctly from the command line. A Docker that checks we can run a command to check that the Docker is working properly in terms of containers by using the Docker container list command, or Docker container ls works as well. So Docker container list, or ls, if you like to save a couple of characters, allows you to show whether it's running or not. Here you can see there's no containers running, so I just get the headings from the different parts of the table, and it doesn't show any containers running at all. So as it says here, on a newly install on new Docker, it should look something like this, which is what mine looks like, and because there's no containers running. You can also use Docker info, but I'm not going to run that because it's just producing masses of output that's not very interesting. If you get a message that looks like something like this, if you can't connect to the Docker desktop, Docker engine, or however you work through the setup instructions, this means it's not quite working properly. If you run into these problems, please again say something in the chat, or put your hand up and let the helpers know, and they can come and speak to you about that. So finally, so you can also get a lot of help from Docker. The Docker help is actually the Docker online help is actually quite good. So if you use Docker -- help, that's right, you actually get quite a lot of useful information. The key thing of Docker, one of the key things to remember with Docker is that it has a lot of sub commands. Okay, so for example, you saw one of them already when I was looking at Docker container, which was the subcommand for Docker to interact with containers, and I used ls to see if I could list them. But if you add the subcommand and then add -- help on the end, you get the specific help for that subcommand of Docker as well. So the Docker online documentation actually is also really, really high quality. So depending, it can sometimes be a bit useless, but yeah. So Marco, hopefully one of the helpers can come and chat you. That means the Docker's not running, not running yet on your system properly, or it's not been started. So there's a lot of help there. The online documentation with Docker is actually quite good, and hopefully once you've been through this course, you understand enough the terminology to be able to read the documentation and understand what it's trying to tell you. Okay, so we talked about that. and how to get help that way. For example, and you can even go even further. For example, we use the Docker container list. Yeah. So yes, if you're running with Linux, I think you need to. There are a few extra steps, and there's an extra step to set it up with. You can either run the Docker command with sudo, so sudo docker container ls or something like that, or there are steps on the Docker website that show you how to set up a special user for Docker on Linux, and then add the right privileges to your normal user, so you can access it without the sudo command. It may be easier just to use sudo in the short term, but we'll find the link to how to do the setup and put it in the Etherpad. Jeremy, if you can, do you know where that documentation is on the Docker website? Because it might be useful just to pop that in the Etherpad so people can see it, how to add Docker,
I will find it and post it in the chat and drop it in the Etherpad as well.
Great, thank you. Okay, so you can also go a step down even further with the help. So, for example, we can do the Docker container ls, and you can also add minus help there, and you'll get the specific help for that site, for that part of the command as well. So the Docker help actually works quite nicely. So there's one brief exercise here is to run Docker help, pick a command from the list, explore the help prompt and the command, and try to guess how the command will work, but looking at usage. But before, or if people want to do that, that's great. I'm going to put a quick poll up because I just wanted to get an idea of how many people have working Docker and how many people are having not working Docker. And I will, just to get an idea where people are with that. So if people want to look at the exercise while I put the poll up, that would be really handy. I just want to get an idea of where people are up to.
I do HPC, so I'm of course obsessed with performance, and I wanted to know. So I've started using Docker just in the last week because of the dependency help. So this was a very the timing was fantastic, and I wanted to know, for instance, what's the actual overhead of deploying the user space from the images. And what's the impact of using a different image? Like maybe I can use the Ubuntu image, or maybe I can use a Rocky Linux, Clear Linux, Alpine, or whatever. And I don't see how these things can have a huge impact or a small impact. I have no intuition on it.
Okay, sorry, I just realised I was muted when I was trying to speak. But I generally, my experience, Jeremy and others might have other things to say, is that actually the overhead of using containers, the performance overhead using containers is very low. Right? I mean, we'll talk a bit. You'll see this a bit more tomorrow when we talk about Singularity on HPC systems and using MPI with Singularity, and you'll see that actually you tend to get back the native MPI performance within the container that you would have had if you were running out with a container on the HPC system. So actually, the overhead is generally very low. It's not zero, but it is. I think people have shown it with MPI. The overhead's generally less than 5%, definitely less than 10% in terms of performance of message passing anyway, which is one of the things you'd expect to be the worst because you're going out through the network interface. Okay, the reason for that is actually because it's really using the same Linux kernel under the hood. So the container just sits on top of the common Linux kernel that's running everywhere. Now, the one difference you may see is that if you're not on an HPC system which is running Linux natively, say I'm on my Mac, which obviously doesn't run Linux natively, then the Docker desktop has to run a version of Linux and then run the containers on top of that. So I would expect more performance issues when you're running, for example, on Windows or Mac, where there's this extra layer in between you and the kernel. but less so on Linux systems where the kernel actually natively exists on the system.
Cool. Thank you. Interesting.
Sorry, what I said was I was going to carry on when I was muted and chattering away to myself quite happily. I said we'd carry on with the next section. That'll take us to a break. I know there are a few people who are still having problems with their Docker install. Hopefully the helpers can continue to help you out with that. And as I said before, the recordings and the materials are always going to be available, so you can always run back and go through it. Or you could just, say it's not working at the moment. I'm happy to listen in and see how things go, and then follow through myself at a later date. Certainly Jeremy and myself are always going to be available. Are always happy to field questions after the course is finished. We're happy for you to email us directly with any questions you might have if you weren't able to quite follow through during the course itself. So we'll move on to the next section, which is about exploring and running containers. I just wanted to remind you that there is a difference between the container and a container image. And typically, I'll try to be very, I'll try to be careful about how I use them, but I may slip up. Okay, so apologies if I do that. I won't always say container image. I will often just say image instead. That's typically how it's used in real life. So that's that's actually how people use the terms. So we're going to explore our first Docker container. Docker team provides a really simple container online called Hello World, and we'll start with that and try and get hold of it. So we're going to download it first. So let's start with showing what images I already have. So Docker image ls. Okay, so I already have some images here because I've got a pre-existing installed Docker. I did have a cleanup, so it didn't look so horrible when I ran this command. But there are a couple of things I didn't want to really delete because it's taken me a while to get it took me a while to download them. I have two things here, two images. Just to say, one of them is for building documentation, which we use for building the ARCHER2 documentation. It's a tool called Material for MK Docs. And the other one is the focus of tomorrow, which is Singularity, is an image that potentially allows me to work with Singularity. But so the Hello World image isn't there already. So to get the Hello World image, there's this sort of magic Docker pull. There's this kind of Docker pull to get the image, and then the name of the image I want to get, which is Hello World. So let's try that and see what happens. Okay, so hopefully, if you do the same, you should see some sort of information here. The same sort of information here. So you get this sort of output. What does it actually mean, and where did it come from? Well, somehow Docker under the hood knows to go to the Docker Hub and get images. Now, the Docker Hub isn't the only service that provides Docker images out there. But it is the default one for Docker. So if you do Docker pull without any other information, it's going to go and look at Docker Hub and try and get that. And if you don't provide, there could be different versions of images, which is the tag thing here. If you don't specify that, it tries to pull the latest one for you. So what this did is it went to the internet, found Docker Hub, looked for an image called Hello World, and pulled it back to install on my computer. So now if I do Docker image ls again, you'll see that as well as the two I had before, now Hello World is here as well, and it's been downloaded into my Docker installation on my system. Okay, so there's an exercise here, which I've just showed you the answer to, unfortunately. Sorry, I should have skipped ahead, but Docker image shows you what images actually exist locally on your host system, and they've already been downloaded there. And of course, if I type ls here, I've got something called a folder called saved images on my system. But that's not where the images are. That the saved images one is actually where I downloaded the images beforehand to put in the data sync link in case people are having problems connecting to Docker Hub. Okay, so that's not where it's putting them. So Docker desktop has some place somewhere on my host computer where it stores images and looks after them. It doesn't just download them into the folder I'm working or the directory I'm working in at the moment. Okay, so you have to use the Docker image command to see what Docker images you have on your computer, because they're not just in the file system in the location where you are by default. It stores them in a special place. So now we can try actually running the container. So let me try running that. So similar, again, all the commands start with Docker or sudo Docker sometimes if you're working on Linux, but Docker run hello world. Okay, and it actually produced some output. So it looks relatively simple, and it was relatively fast. And I don't know, I mean, maybe people have used virtual machines before. And when I first started using containers after using VMs for a while, that was the first thing that surprised me so much, was how quickly things happened with containers compared to the VMs. Was that you got the information, back almost instantaneously. So this shows that installations are working correctly, and Docker it tells you what Docker actually did. Actually, our pull was in a separate step, but remember that this was the image we pulled. So what's happened now is that Docker has used that image to create a container instance, a cookie from the cookie cutter, and then run the container, which then produced some output, which pushed it, and the output came to my terminal. And it gives us a suggestion to try something more ambitious, but we'll ignore that from the moment. So what happened here? It started the running container based on the image. This is the stamp from the cookie cutter. If the container had a default action, in this case, the container's default action was to print that message we've just read. And then it shut down the container afterwards. It finished doing its thing, so it was shut down, and it gave back control back to the host computer. Okay. And the hello world container sets to run an action by default, which was to print that message out. Also, it's worth noting, you could have skipped the Docker pull step. So you could have just gone Docker run, and if the image had not existed locally, it would have pulled it. It would have pulled it automatically for you. So the pull step would have happened automatically. So you can just avoid the pull step if you want. But maybe you're going to be working, say, on a train or on. So say you're working on a train or something like that, where you may not have internet access, you could pull the containers you might need to do your work before you leave, and then they're available on your host computer, and you can just work with them without having to have access to the internet. So you can pre-download sorry, see there, I told you I'd fail at getting the images right, the image container thing right. You can pre-download the images, so you can work with containers when you're away from the internet if you want. Okay, so what if you want to do something different with the container, though, other than the default action? So let's try using a different Docker image to explore what we can do with the Docker run command. So the suggestion above was to use Ubuntu in the output, but actually Ubuntu is quite big. So we'll choose a different type of Linux called Alpine because it's a bit quicker to download here. So can you try downloading and running the Alpine Docker container? You could do it either in 2 steps, or you can do it in 1. So I'll give you a moment to have a go at that, but probably just a couple of minutes, and then we'll work through it together again. So have a go at running the Alpine Docker container and see what happens. Okay, hopefully you managed to have a go at that. But let me have a go here. So let's just try Docker run Alpine. So it tells me that it hasn't got Alpine locally. So it's going to do pull and download and run, but nothing actually happened when we ran the container. So the reason for that is that this container does not have a default action. It's designed for you to be able to provide commands to it itself. So for example, you could, as it says here, you could check what version of Alpine is with what version of Alpine is in the image or the container you're running with Docker run Alpine. Oops, I can't spell. docker run alpine cat etc os release. Okay, and this tells you that when in the container, when you're running in the container, it's Alpine version 3.1.4.0. Okay, so the Alpine Linux, I mean, although I run on a Linux-like system because it's a Mac OS, actually these commands I'm running are actually running in Linux, and in the Linux, in particular, specifically in the Linux in the container. Okay, so can you run this container again and make it print a hello world message? So can you make the Alpine Linux container print a hello world message? So hopefully, I don't know how familiar you are with Linux command lines, but hopefully you may have heard of the echo command. So in Docker run Alpine, we can use echo to echo a message, and let's give it the hello world, the sort of canonical first program. And so this is not my system, which could also do echo hello world. Okay, printing it. But in this case, this output is actually coming from the container itself. Okay, so it's running on Alpine Linux within the container rather than on Mac OS in my native terminal window here. So as well as Docker run, if a container has a default action, just being able to do what the default action says, you can provide commands at the end to execute instead of the default action. And we'll see a bit more of this later when we talk about building our own containers, about how you build in default actions and how you can overwrite and how you can make sure they work properly. So the final, I think one of the final things in this section is running containers interactively, right? Because sometimes you might not just want to use it like this with running the Docker run command every time. You might just try some things out within the container itself, you know, with it, and have like a shell command prompt within the container in the same way I do here in my terminal native system. And you could do that as well in Docker commands. Docker containers. So this time you're doing Docker run again, because we're running the container. You're giving it the -i option, which is interactive, and also the -t option, which is to assign a TTY. It's a bit technical, but that just means I'm going to have a terminal that I can interact with. It can pass information backwards and forwards on the container. The container image we want to use. So Camilla said, printing Docker run Alpine hello world with an exclamation mark, which is not specified in the example here. So if you had an exclamation mark before, I found this the other day as well, because typically you put an exclamation mark in the whole hello world example with programming. That it's essentially escaping the second inverted quote, double quote, the second double quote. So it thinks there's no double quote on the end of your command. So if you just type dquote another double quotes command, it should, and press return, it should close the command and make it work, hopefully. But there's something going on with the exclamation mark that's escaping the double quotes on the command line that's causing that confusion. So if you see dquote like that, it just means there's some unclosed double quote somewhere in the command you've just typed, is what that typically means. Sorry, so but back to the interactive command. So we're running Docker interactively, we're assigning a TTY, and the image we're going to base the container on is Alpine. And then we do need to give it a command we want to run. And the command we want to run here is to give it a shell. Now, typically, you might automatically think the bash is the right shell to use, because that is typically the shell that's available in most Linux. But Alpine's a very small version of Linux, very stripped down version of Linux. So it actually only has the Bourne shell, which is sh available in it. So sh is the command here. Okay, but sh gives a it gives you the shell. So as Ross says there, when if you try it with bash, it says event not found, which means that that command's not available. Okay, so let's try that. And you should see my shell prompt has changed from the one on my Mac, which is that funny chevron, to a hash. Typically, if you get a hash shell prompt, it means you root in Linux somewhere. Okay, so Michael said you can get the exclamation mark by escaping the exclamation mark by putting a backslash in front of the exclamation mark if you want. So now I'm in the container itself. You can see if I ls, I can see various different bits of the file system. That's pretty standard Linux directories that you see at the bottom of the file system. And now we're inside the container, so we can try different things such as which directory we're in. Well, we're in / pwd says print working directory. We tried ls already and showed what was there. You can see what user I am. Who am I? I'm root. That's the hash. So that means I'm the root user or the super user within the thing. So we can also print a path which says which directories are searched for commands. And it's a pretty standard thing from Linux. And cat etcos release, which is what the command we ran before, without going into the shell interactively, should show the same thing, because we're essentially running the same thing. We're in the same container. Once we've finished doing our commands and doing what we want to do, we can just type exit, and that should get us back to the prompt on the host system again. So you can also get into the container itself. So Long asks about why am I not able to RM an image? I got this. Long, if you could just wait to one of the next episodes, we're going to talk about managing images and why you can't delete an image and how you fix that problem. That is actually one of the next bits of the course, and we'll talk about it in detail then. So there's a small, the final thing here before we stop for a break is a little exercise. A little exercise just to try and run the BusyBox a container based on the BusyBox image, and see if you can find out what version of Linux is installed in the BusyBox container. But on BusyBox, you want to look at the proc version command, and also can you find out what the BusyBox program actually does in the container. So I'll give you. So what are we, about 11 minutes past 11, just 12 minutes past 11. Give you maybe 3 minutes to have a go at that. We'll have a quick look at the answer, and then we'll stop for a break and give people a chance to go and get a cup of tea or something like that. So I'll give you just a few minutes, have a go at getting the BusyBox thing running, and see if you can solve these two problems. And if anybody's got any questions, please just put them in the chat or shout out and ask. I'm happy to try and answer them. Yes, Peter. When you're in an interactive container, you just type exit to log out. It's essentially the logout command. So exit the shell, and that'll put you back to the host system. So Matthew has asked a question about how isolated are containers. Connected to security. Can there be malicious containers that potentially mess with the host file system? So the answer to that is, never say never, right? I mean, but this is one of the key things about containers, is to try and isolate what you're doing from being able to affect the host file system. And actually, although there's no way to say there's no vulnerabilities out there, there's no way for anybody to do that, because all computer systems are vulnerable in a security way in some cases. But Docker is pretty secure. And one of the reasons it's pretty secure is because it's so widely used. And a lot of people have workflows based on it. It's used widely on the big cloud platforms. So it's in their interest to make sure the security is good as well. So most security issues with Docker get fixed quite quickly. And That's not to say there aren't any sort of day zero vulnerabilities out there or potentially new vulnerabilities coming up in the future. But it's as secure probably as any other piece of software. Now, of course, there's a chance that you can do more malicious things because essentially you're escalating to root here. So if you can cause problems from a container, you have potential to do more damage because you are root essentially on the local system. But generally, I don't think it's any less secure, particularly than any other system. There is maybe the potential to do more damage if you got through through there. But then, any operating system has potential. I think you have to presume that any operating system has holes and bugs and security issues in it anyway. So Docker's no different. But we will talk a bit about this, actually when we come to look at Docker Hub a bit later on this morning as well. How do you assess, what things can you do to try and assess how trustworthy the random image you're using off the internet is? And that is a key thing here in terms of security is having some way to assess or think about, how trustworthy is the source of the image that you're going to run. Nicholas asks, is there a way to see a Docker file of an online image? So the answer is yes. Not so. What am I trying to say here? One of the ways you can assess the trustworthiness of an online image is that they publish the Docker file along with it. Okay, so even one of the things I would look for before I was downloading a random image off the internet, I think, is does the Docker file exist? Is the Docker file published on Docker Hub along with the image itself, or whatever the online source of the image is? Okay, but we'll talk about a bit more about that in a minute when we talk, or a bit later when we talk about Docker. Let's finish off so that people can have a break here. So in terms of the BusyBox, command here. So actually, it's pretty similar to what we've done with Alpine, except that I'm going to try BusyBox here instead. Okay, so let me get this will give me an interactive. Should give me an BusyBox. It should give me an interactive shell within the BusyBox container. It'll tell me it can't find it locally because I haven't downloaded it before. And there you go. I've got my shell. So what was it? /proc/version. I think, was it not? Yeah. So okay. So it's based on Linux 5.10.25. Okay, and what does the BusyBox command do? Well, the obvious way always I think to find out what command does is to give it the help option and see what it says. And it says BusyBox is multi-core binary commands, binary common Unix utilities to a single executable. So it gives you a way to have a command that can run lots of things that you'd normally have available in Linux as separate programs. All built into one binary, so that it's easier to distribute, and you don't need the whole Linux distribution to actually be able to run all of the commands. Okay, so let me get out of there as well. So that's the end of that section, and it's very basic there. But we've seen quite a lot about Docker pull and getting images, particularly from Docker Hub. How to look at what images are already on our computer with the Docker image. The Docker run command and different forms of the Docker run command allow us to run different commands, allow us to gain an interactive shell within the container. So actually, we've covered quite a lot of ground in even that basic section. Hopefully, you've got a better idea of how containers are actually used in practice a bit. So we're going to have a break now until 11:30. That gives us just over 10 minutes. So please do go away, get a coffee, tea, drink, stretch your legs, whatever you need to do. We'll come back and start again at 30:30 sharp, and we'll take a look at, as we've just been talking a bit more about Docker Hub. And then after that, we'll talk I know there were questions about deleting images and things like that. That's the next session after that as well. So we'll do that after our break. We'll see you back here at 1:30. If anybody has any questions or is still struggling with Docker installations and things like that, please do let us know in the chat, and helpers will keep an eye. Myself and the helpers will keep an eye on that and help you out as needed. Okay, there's quite a few people back now, so we'll get started in the interest of time. I see we've got a question from. I know Andrew's asked about setting up rootless daemon, and so if anybody's had any experience with that, that'd be useful to hear. I have to say I've not tried that because I'm always on Mac anyway. Yesel has asked, what's the difference between a Docker container and a Docker image? Right, and it's worth reviewing this. The image is the description of how to create the container. Okay, so a container, as Joni says, container is an instance of an image. So you have one image, but you can have multiple containers based on that image. You say, so I may have one hello world image, but every time I run the hello world, every time I run it, I'm creating a new container based on that image. Okay, so there's usually one image and multiple containers. So it's the cookie cutter analogy was the one we used before. Is the image is the cookie cutter, and the containers are the cookies themselves. So you can cut multiple cookies from one image from one cookie cutter. I hope that answers your question. Yes. Okay, so the next little session is on Docker Hub. So it's not really typing commands and things like that. It's quite short. As I said at the start, we're going to finish at midday, no matter where we are, to allow people to have time for lunch, because people might have planned around the published schedule for that. And then we'll pick up again wherever we've got to after lunch. I know according to the schedule, it looks like we're a little bit behind, but I wouldn't worry about that. This is typically what happens. We typically speed up as we go through, because there's obviously a lot of questions people have at the start about the basic stuff, and we really need to make sure we cover that properly, so people have a foundation for what we so they can understand the more advanced stuff better, properly. Okay. And Peter's asked a question. I wonder if using Docker will be able to overcome issues in MATLAB needing different add-ons for different systems. Now, I'm not particularly familiar with MATLAB, so I don't know quite what relationship between add-ons and systems. Do you mean like GPU add-on for using a GPU card and things like that? Is that what you're getting at here, Peter? For example. Okay, I mean, typically there are Docker containers available for things like systems equipped with GPUs for GPU computing. Singularity is the same as was, we'll talk about Singularity tomorrow. And you do have to have those capabilities built into the images to be able to make use of them on local system. So typically images do have to have, for example, GPU drivers and things like that. Okay, but Peter, yeah, okay, I understand that. But there's different functionality within MATLAB that might not be installed by default, and then when you get somebody else's MATLAB, it might not have the bits you need. So container would be able to overcome that, because you could say that so you could package up, say, a MATLAB container, I assume, that contains the add-ons you needed and you used, and then distribute that. But of course, there's complications around licensing and paying for stuff around MATLAB that you'd have to be wary of when doing that. Typically, you see that. I mean, in fact, let's go on with this section, because actually you might see something a bit like that here as we go through talking about Docker Hub. Okay, and I'll try and keep that in mind and point it out if I spot it. Yeah, so Docker Hub. why is it useful, and what do we need to be aware of when looking at images that are available on Docker Hub? So Docker Hub is an online repository of container images that's tightly integrated actually into the Docker desktop and Docker as it's generally installed for people on their systems. So anybody can put images on Docker Hub. So first approximation, you get a free account, you can put your images up. But a large number of the images are actually created by developers of the software they package. So, there's commonly used pieces of software which are provided in some sort of official sense for Docker via Docker Hub. So things like Python and R, the R statistical language are common ones. Docker can be used without connecting to Docker Hub. You can use your own, you can get images from elsewhere. You can actually get images as tar archives and just import them in that way. You can provide your own. You could provide your own repository images, and so some organizations may run a container infrastructure that's entirely disconnected from the internet and from Docker Hub in that way. But let's take a look at a particular Docker Hub page, because they actually have quite a bit of information on. So let's have a look at the one for Python, the official Python distributions. So these are the official images from Python. Let me make that a bit bigger because it's really difficult to read at that size. Give me a second. Hopefully, it should let you zoom. Using the wrong key. Okay. So it has some sort of tags, which maybe try to describe the image when you're searching it. It also it has these sorts of metadata. It often has a description, or at least the good quality images should have a description about what potential versions are available. Sorry, let me scroll all the way down. Some information about what's in the container here about Python and how to use the image. So here it gives an example of how to build your own Docker image, which we'll come to later, built on top of the image, or using the image from the Python image from Docker Hub as a starting point. Okay. So say you had your Python requirements in a file called requirements.txt. This would take the image, the Python image from Docker Hub, install your extra requirements, and then give you an image which you could then distribute out, which was based on the official Python distribution, but with your extra requirements added in. Okay, and it has all the information on how to use this image. You can use it to run a single script, and some more information about what the different image variants and things that they provide are here, and some information on licensing. So the good quality images will often have quite a lot of information there. You could also look at the tags tab, and this will show you the different versions and the different and what's available on the system. So you can see they distribute various versions of the Docker image for different architectures. Okay. Within the Python one. Okay, so and sorry, the other bit I didn't obviously point out was that back on the main page, if I go back to the description, the first thing it shows you, or up in the top right of your browser window, is a bit bigger up here, gives you a command that you can use to actually get hold of this container. Right, it's very simple description here. And often examples of how to use the image. Yes, sorry, Long. Yes, the OS Arch refers to the host. So if I go back to the Python here, where was it? Same Buster, I assume all of them. So they do various ones. I mean, obviously one. Sorry. Oops. Can I get rid of that annoying thing that's just popped up in the way? Let's get rid of that. Yes, so these are the different host architectures that they provide the image for. Now, one thing that I've run into is because I've got a UMac, it's actually ARM-based. It's an M1 processor. So some image providers don't provide ARM v6, you know, or sorry, ARM, the right ARM images to support it, but the Mac can natively do the translation on the fly from the sort of the x86 to the ARM process. But that's sort of by the by. Yes, it will try to use the right OS and Arch according to your machine when you try to pull the tag. We might see it later when I try to pull some things on my system. You'll see that it can't. It might say some of them where it can't find the right OS Arch, and it'll warn me that that's the case. So Nicholas asked me, you know, if they've got pre-compiled codes, is it possible to use that as a base to obtain the image that's tailored for your machine using your machine type? So if you take an image and then recompile your own binaries in it, that's fine, right? You can provide, you know, as part of the build process, you can compile whatever you like and add whatever compile flags you like. That's up to you. You can't change the binaries that are in the image as distributed straight away. Okay, but you know, yeah, with the image, you get the binaries as they are. Okay, you could use that image as a starting point to build your own images and add additional versions of the software that might be tuned. That's fine, because then you can compile them yourselves. But you know, you can't change the binary in the image in the same way as you just can't change a standard binary that you just get hold of. If somebody gives you a binary, you can't tune that generally for your own system. Because you don't have the source to recompile it. Yes, you'll see that certainly tomorrow when we use the Singularity images. You'll see how to use it as a compilation base. Okay, so in the versions that are available on the Docker page, you know, there's many different versions of the container images based on different software, and they're usually in this format with container name and tag. So, for example, for Python, you could pull a particular version of Python with docker pull Python : 3.8. But if you wanted the 3.6, you'd replace the 3.8 with the 3.6. The default tag, if you don't specify one, is always called latest. So if you don't give it a particular tag, then you get the latest one. So far, you know, if you see the Python one, it's maintained by the Docker team, you know, but you can use, like I say, anybody can upload images to the Docker Hub, so you can use any of those containers from the Docker Hub, you know. So you also get containers managed by people like Continuum.io, the people who distribute Anaconda, or Rocker, a group that builds community R containers and things like that. And they typically have this sort of slightly additional extra piece of information in their name. So they'll have the owner / container name and then tag. So the technical name for this is a repository, which is really confusing because it's not like a Git repository or the sort of repository you might have come across before. The tag indicates a specific version of the container image you'd like to use from a particular repository. So, you know, in this case, actually, what this really means is owner repository tag. Okay, and if we looked at the Docker container produced by the Rocker group, that has version 3.6.1 of R and the tidyverse installed. So if we look for Rocker in Docker Hub, let's see if we can find the Rocker people. Yeah, so let's see how this works. Okay, so here's Rocker. Here, so let's just follow the Rocker thing. So they have various different ones, different repositories, and one of them is the tidyverse repository there. And I can't remember the exact thing. And we wanted 3.6.1. Okay, so let's have a look down here and see what tags they've got. So there's a latest, there's a 4.1. You can scroll down. There should be a 3.6.1 hopefully somewhere. There we go. So to pull that one, the command would be docker pull Rocker, which is the owner. Tidyverse is the repo or the container name, the container image name you can think of it as, and the tag and the version is 3.6.1. Okay. So, you know, there's a lot of stuff out there. on the Docker Hub. And one of the actual questions that was asked earlier here is, you know what, it was about trust and security. And one of the key things you can do to protect yourself is be careful about what images you use and run. And part of that is experience, and part of that's just getting used to having a look at Docker Hub or wherever the container is hosted, and understanding what sorts of information is there and making an assessment based on that. So, you know, the sorts of things you might want to look for are things like that the image is updated regularly, you know, that isn't ancient and old and seems to have died and withered, in which case it won't have received any security updates and things like that. The image is associated with a well-established company or community or other group that's well known, such as the Rocker people or Continuum.io, or as an official container provided by the Docker team, in which case, you know, it makes it much more trustworthy. There's a Docker file or other listing of what's been installed into the container. So if we go back here, let me see if I can find where the Docker files are, the tidyverse one. So in some, okay, let's follow this to the source. Maybe I'll be there with the, it's maybe quite hard, a bit more difficult to find here. So let me see if I can go back to the Python one. Description. So I will need to go right away. I thought the Docker file used to be just listed here on the page, but maybe it's vanished, and maybe I'm just being silly, because I thought the Docker files used to be listed there, or used to be shown. Ah, here it is. Okay, so when you follow through from the various tags here, so say Slimbuster, then the proper ones will show you the Docker file. This is essentially the Docker file here, okay, and shows you what they've used in the Docker file. So, you know, if they publish that as well, that gives you more confidence of what is actually associated with the image. And the image page has documentation on how to use it. That shows that it's got some care and it's supported, and people are taking it seriously. You know, for example, if you see a container that's never updated, created by a random person you never heard of, and does not have a lot of metadata or documentation or anything associated with it, then I would be much more cautious about downloading and using it. You know, and even if such a container is secure and you know is good, actually it's more difficult it's going to be more difficult for it to be reproducible anyway, because you don't understand what's in it anyway. So it sort of defeats some of the positives of using containers for containers in a reproducible way. You know, so if you want to, at some point you can have a look through Docker Hub and see what's there, or you'll see other repos, other websites that contain Docker containers. It's the Docker images in the future, probably in the Singularity lesson. We'll see Key.io, for example, which is one that's maintained by Red Hat. But have a look and see if you can find something that's useful to you and interesting for your research. There's actually a huge amount of stuff out there, you know, and so much so that now, you know, if I get to a stage where I think, oh, I need that tool, so rather than install it now or look at how to install it, the first thing I'll often do is go and see a search if there's a Docker image, you know, that I can just short circuit the whole thing and not worry about the installation at all, and just not have to engage my brain in that way, and to look at installation. I'll see if there's a Docker way to do it instead first. So yeah, I mean, you just have to be a bit careful. There's lots of stuff out there, but in the same way as using any software, be careful about what you're using, and make an assessment of how much you trust the source of the thing you're going to use. Right, so we've got a few minutes left before we're going to stop for lunch, and hopefully that's giving you a bit of an idea of what Docker Hub is, and actually that there's a lot of content out there that's available to you just via the Docker pull command if you've got Docker installed. So Long asked earlier about removing containers and removing images. Okay, so we've got a quick little section here. We might not quite finish it before lunch, but in case we'll just pick up after lunch. But as Long said in the chat, I don't know if people saw it. If we do a Docker image ls, so let me make this a little bit small, a little bit thinner. Oops, sorry, struggling with my Windows. So Docker image ls to show all the images I have. So let's try and remove the hello world image. Now, one of the key things we want here is this image ID. So let's try that. Take that. I'm going to copy that into the clipboard. I'm going to go Docker image remove, and then the ID of the image I want to remove. You could use the name as well, but sometimes the ID is more unique here. Okay, and you see the image that Long put in the chat, which is unable to delete because the image is being used by a stopped container. Okay, so what that is saying to us is that there are containers left lying around. Remember, containers are instances of images, and there are containers lying around that are still using this image, so I can't delete this image. So actually, we need to see what containers are running and make sure they're tidied up before we can go and tidy up the images themselves. And in a similar way as the Docker image ls command, we can use Docker, oops, if you can spell Docker, like me, Docker container ls command. And, okay, there's something odd here. It's not showing me any containers, okay? The weirdness here is because what that command does by default is show you running containers, okay? And most of the containers that we've been using have ran and finished, okay? So so to get around that, to show all of the containers which have been halted or which are running, I could do Docker container ls --all, okay, so to force it to show me everything. Now, if I do that, I get a much bigger list. And let me make this a bit wider so it's a bit easier to read. And you can see that there are various ones, and you can see that their status is exited. Okay, and so the hello world one is down here at the bottom because it was the first one we did. And you can see it exited 55 minutes ago. And this is the container, the instance of the image that's stopping us from deleting the image. So let's get rid of that one and see if that helps us out. So sorry, what we want is Docker container, because we're interacting with containers. We're interacting with the containers, not the images at the moment. RM. Okay, and then long as is there any reason that Docker keeps the stop container not on? So the reasoning is that if a container is just stopped, you might be want to use it again very soon, and it speeds up the restart of the container and makes it means that you don't have to rebuild, recreate an instance of the container from the image. You can just restart that same one. You'll see a bit later that we can provide an option to the Docker run command that tells it to automatically delete it when it stops. Okay, but it doesn't do it by default. You have to have an extra command to the Docker run command. But so now we need to specify which container we're going to delete, and we can give it the ID as before. We'll also see that it generates a random name for the image. You could also use that to delete it. And in fact, I quite like doing that because the names are sometimes funny, and everybody needs as much fun in their day as they can get. So some of the names are a bit funny, and I quite like using them to delete the container. So I'm going to Docker container RM Reverend Beaver, and it echoes back the name of the container to me to tell it it's done something. And if I go and ls now, all, you can see that the hello world container is not there. So let's try now Docker image ls again. I'm going to go Docker image RM and take the image ID for the hello world image. Okay, and this time the delete worked because we'd removed the container that was associated with the image before we deleted it. Now note, if I'd run hello world lots of times separately, I would have had multiple containers relating to that image that I would have had to delete it before I can delete the image. If you get to the stage where you've got a lot of containers left, oops, sorry, of course I missed the minus all, left just sitting there, exited, and you're like, do you know, I really don't want to go through all of them and delete all of those containers. It's just going to take me ages. You can use the Docker container prune command. That will delete all of the exited containers and tidy them up for you. You have to be careful a bit, because if you had one there that you still did actually want to leave exited so it could start up quickly, then you would remove it with this. But Docker container prune will tell you this will remove all stop containers. Are you sure you want to continue? The answer is yes. Okay, and it's done that. So let's Docker container ls, and you, oops, sorry, minus all. You can see there's nothing there anymore. Okay, if I log off, will containers end? Oh, I haven't tried that, Mark, because with modern laptops, you hardly ever switch them off anymore. So I haven't tested that. Potentially yes. I would suspect that, but maybe also no. So I would have to test that and see what happened. I don't know the answer. If any of the other helpers know the answer to that off the top of their head, I'd be interested to hear it. Okay. So we've run through all of that, removing the exited container, pruning them. We removed the image at the end. So actually, we have just made this by 12 o'clock. So hopefully, that answered that question. Yeah, and this is just a little bit of management. Is, you know, what containers do I have running and exited, and which images are still sat around waiting to be deleted. So one thing I can show you is there is an option, and we'll see it later, that removes the container automatically when it stops. We can find out what that is by docker run -- help, and that should show us all of the different options. And the option you're looking for here is --rm. Okay, so if you add --rm to your docker run command, it automatically removes the container when it exits. Okay. Yeah, so if you add the --rm, so if you did something like, I don't know, where are we? Oops. If I did docker run --rm hello world, now I've deleted the container and the image, so it's going to have to go and pull it from Docker Hub again. So it should do that for me, because it tells me it's unable to find the image locally. So off it goes, it runs it. So the container ran that time. And if we do docker container ls --all, there's no container there anymore. So we can do docker image ls, and the hello world one's there again. So let's do docker image rm, and it's this one. And it just deleted that time because the container wasn't left lying around exited, because I added the --rm flag to Docker. Okay, so that's taken us to midday, and I promised we would stop for lunch here. As I said, we caught up on the schedule. After lunch this afternoon, we're going to look at how you create your own container images. So not just use things that exist either on the Docker Hub or in other places, but how you can create your own ones that contain the tools and things that you're interested in using, and then how you make them available on Docker Hub and various other ways. Okay. I'll stick around for a little while. I'm happy to answer any questions people have, but I do want to make sure people have the full essentially hour and a half, because I know that online you need those breaks to be able to keep concentrating in the afternoon. So we'll see you back here at 1:30 UK time But like I say, if you've got any questions, feel free to ask them now. I'm happy to stick around and answer questions for a wee while before I go and stretch my legs too.
Yeah, thanks, Andy. Just to say that I'm also happy to stick around if anybody's got any questions, or particularly if you've got any technical issues trying to run stuff that you didn't manage to resolve in this morning's session. Do let us know. I'm very happy to provide assistance if you're still struggling to get things working. Otherwise, have a nice lunch break.
Thanks. I might have a really small one. If possible, is there a difference in the kind of operating system you download for your image? Like I've seen many people use Ubuntu as a base one, but I've seen other more performance-driven, such as Clear Linux, Rocky Linux, and if the container runs only on the kernel, is there going to be a big difference? Like I've seen some claims saying that there can be a performance difference. I don't see where it can come from besides default flags.
Yeah. So that's a very good point. I mean, I guess, as you say, if you're sharing the main system kernel, then there's a limit to some extent. Obviously, at the level of any sort of kernel optimizations, you're not going to get any difference. In terms of specific kind of real-time Linux operating systems or whatever, yes, I guess it's true that most of those changes come from the kernel itself, but there are obviously potentially things that can be done in individual software libraries to optimize them to give you some small increase in performance. I guess the main reason I suspect that people tend to use Ubuntu or other sort of widely used distributions as the base is just that those distributions tend to have more up-to-date images with better support. The libraries are more up-to-date. There's so many packages in the sort of package ecosystem that are updated frequently. So it's more that kind of, I think, just having something where everything is up-to-date and you've got more chance of being able to get the software that you want already packaged from the repositories. Whereas if you go for more obscure distributions, then perhaps there isn't such a wide package ecosystem and you might have to start building things from source and all the rest of it. So I think that's a really good question. I don't think that there's likely to be an absolutely huge difference. I haven't done any performance tests myself, so I can't be sure, but I suspect that you're probably quite right that a lot of this stuff comes from the kernel. So yeah, I think it really is just down to, if you've got use cases where you're working with software that requires a specific distribution because you're doing something specialist, then you can probably find an image for that and you might use it for that reason. But otherwise, yeah, it tends to be, as you say, people tend to use Ubuntu, Debian or whatever as base images, depending on what, if you're more familiar with CentOS or that kind of package ecosystem, then you might use that. But that's really, I think, ultimately where, what the decisions that people make.
Cool, thank you. And sorry, just because you mentioned, are there any kernel-specific configurations that have any kind of big impact? This is something that I'm pretty ignorant about, but I hopefully one day want to learn. Like maybe the frequency update. I don't know, the performance governor. No idea.
Not so much anymore. In the past, HPC platforms may have taken the Linux kernel, or may have, so a long time ago, each HPC manufacturer essentially had their own operating system. It was back in the day, IBM had their own Unix operating systems. IBM had AIX and Cray had Cray OS, and there was various other ones. Some of those ones still exist out there. AIX is still there, and the HPE version is still out there for their mainframe systems. But since HPC systems have all moved to Linux, essentially, there was then the next step where a few of the different vendors would take Linux kernels and then optimize them for the system. So they'd take out things like Bluetooth, right? Who needs Bluetooth functionality in the kernel when you're on the HPC system and things like that? Actually, even that's died away now, right? And the reason for that is that one, the Linux kernel has generally got faster and faster and sort of better and better performing as time's gone on, just because that naturally happens if people develop it. Obviously, there's the opposite where you get some sort of bloat of features added into the kernel, but also it's become a lot more modular. So you know, if you take the default kernel, you can tend to add in different kernel modules for things, so it tends to come in a bit more of a lean form than it used to. And also processors have just got so fast that actually the gains you get from optimizing the kernel are so small that it's just not worth it. When you know, on most HPC systems, you know, people are really interested in performance, but you know, the difference in a compiler flag for compiling your software, or between using, say, Intel's MKL versus AN other numerical library, can make of the order of 50%, 10 to 50% difference. The marginal gains you get from actually doing any work on the kernel just aren't worth it in terms of return anymore. So almost all vendors do nothing to the kernels anymore because it's just not worth the time and effort. You don't get enough back. You know, so I think the other thing that's happened actually, of course, over time is that the kernel's always compiled using GCC. And GCC has become a lot better as a compiler from the olden days of version 4 to now where we are up at version 10 in terms of producing performant code. And part of that is the drive to have the kernel be faster. I mean, that's why GCC has got better a lot of the time. So all of these things are pushing to the fact that actually messing about the kernel is just not interesting anymore in terms of performance. So first approximation for HPC systems, because other things make so much more difference. I don't know if that answers your question, but it's a bit of a diversion away from you know, which OS should I choose in my container. I think the fundamental answer is it doesn't make a huge amount of difference. It may be that because of the size of the OS, there's some performance overhead in loading up the in terms of loading up the container, or getting the container started, and then also the amount of memory it occupies, which may lead to inefficiency. But so you might want to use a lighter weight version of Linux to control memory usage and to improve startup. But then, you know, if you have a startup time difference of even, you know, a long startup time for a container is like a minute, right? I mean, that's a huge startup time. You've been seeing the ones we've been running here, you know, how instantaneous they are. I mean, it may be longer if, you know, 1,000 processes are all trying to do it at the same time. But even if you had a minute and your job runs for 48 hours, who cares, right? To a first approximation.
Okay.
You know, it's a case of, you know, one of the things we teach, actually not on this course because this is about containers, but one of the things you teach often about when you're doing programming courses, particularly on HPC, is premature optimization, right? Don't worry about optimizing the things that you don't know are a problem yet. You know, so you can imagine lots of things might be a problem for performance. But the first step actually is just do those straightforward things with a standard set of good starting points and see where you get to. And if the performance isn't good enough, then start worrying about where you are, rather than trying to do this sort of, because you might spend more time worrying about optimizing things that actually have no impact. So you might just end up wasting your time. And I think I'm not saying there's nothing here, but it does feel a bit to me like this is one where I'd want to just do the basic sensible thing first. And if the performance looked poorer than I was expecting, then I would go and look deeper. But the performance is pretty good to start with, then I sort of feel like, well, there's better places to concentrate my effort.
Yeah, I think I'll take the takeaway message. I'm comfortable with working with Ubuntu. I might just stick with that.
Yeah, like I say, I think the biggest problem with that is going to be memory based rather than performance based. Ubuntu is quite a big image, so you know you may, especially on modern HPC systems where you have in CPU space systems anyway, like ARCHER2 we're going to be using tomorrow has 128 cores per node. Right, and each of those cores is running a copy of essentially a container because you've got an MPI version of Ubuntu. Then memory potentially starts to become a problem. So you might want to look at leaner versions of the OS for to be able to save memory.
So I started getting curious about this because the the Japanese computer, the #1 top 500,
Yeah.
uses they use a special kernel when they not in the login nodes, but in the swarm. They have a special Mac kernel that actually isn't much too different than what you would obtain by deploying a small kernel, I guess, in the computation nodes.
So they have special considerations, right? And I think, you know, if you talk about that system, particularly, it's odd in a number of ways. But one of the reasons it's odd is it has very small amounts of memory available because it has high bandwidth memory. So it doesn't have any standard DRAM as you'd understand it. What it does is it has memory soldered directly to the processor, to first approximation, or integrated with the processor, and has a very small amount of memory. So then suddenly, actually, this becomes more important because your Linux kernel has to take up a small amount of memory as possible because you want to actually use as much memory as possible for the actual programs you're running because you're short on memory anyway. So then it starts to make sense. The other thing, of course, with Fugaku is it's ARM based, right? It's not an x86 processor, and so there's a lot less work gone into optimizing kernels because almost every like proper big system or you know, system that people use both in terms of HPC and in terms of desktops is x86. So everything is pushed towards optimizing for x86. That means you might need to do something more special for ARM. Now that's changing, right? Both in consumer side and in HPC side. There's a lot more ARM HPC systems out there, like you say, Fugaku and various other ones. There's a system in Bristol, which is ARM based. You know, there's a few around. We've even got one in Edinburgh that's ARM based as well. And with the move of Macs to ARM based processors, actually in consumer electronic, you know, with it pushes it into that side of things as well. And other people are using them, you know, NVIDIA talking about developing ARM-based processors, Google as well. I'm not sure exactly what their Tensor Core is, but I suspect it's ARM-based, probably at some level. So, you know, there's a lot of interest in ARM, so that's going to become much more mainstream. But those sorts of specialist bits of hardware are where kernel work maybe does make more sense.
Okay, thank you. Thank you very much.
So Mark's asked the question I don't know the answer. Is ARM still RISC compared to CISC? Pass. I could go and look it up for you if you want. I'm not sure. I'm not sure, actually. I'd have to go and look.
I don't know if Jeremy is there still.
I am, yes.
Hello, it's Chris.
Hi.
So I guess I was thinking about it from the Singularity model, which I'd volunteered to. When Andy first said about the course, I'd kind of vaguely volunteered I might teach one bit of Singularity tomorrow. But in the Singularity, of course, you don't have this kind of hierarchy of images, and I think because I don't use Docker, I think that's what confused me.
Right. Right.
So yeah, it's like there's this hierarchy, so that if you've got a image, so I was thinking about I think I was thinking about the image as being the equivalent of the definition file, but it's not. You've got a build file as well below that, so you've kind of got 3 levels in Docker, where you've only got 2 in Singularity, I guess.
Yes, I mean Docker. I suppose you've got your Docker file, so that's your kind of definition, right? That's what's going to go into the container, into the image. Sorry,
Yeah.
and then you've got the image itself that gets built from that, which is this kind of layered structure. So you've got effectively a kind of base set of files in one layer, and then you've got layers that get built on top of that for every change that you make. I mean, we're obviously this. I guess Andy will go through this after lunch anyway. But yeah, I mean, you've got that kind of the layered structure there. But then I think that's effectively the same as your image in Singularity. I'm trying to think whether.
I think in Singularity, don't you have a definition file, which is basically the equivalent of a Docker file?
You do, yeah. But I'm saying I think that the two are effectively the same. So you've got a definition file in Singularity or a definition file in Docker. It's just that the way that the image is built, or the way that the final image is kind of represented, is different. So I think in Docker you've got like a kind of manifest, haven't you, or something like sort of an image manifest.
So a Docker image is made up of layers, and those layers can be common across images. So if you have 2 images on your local system, both based on Ubuntu, the layers across the Ubuntu image will be common across those 2 images, so you only download them once. Now, because Singularity represents images essentially as a file, they are just a file. There are layers internally, I think, within the file, but it doesn't get reused in the same way because each image is represented as a self-contained CIF file. And you'll see if you pull from Docker Hub, you'll see the text of how it you'll see it converting images to blobs and then incorporating them and then pull them all together into a single file and splitting it out as a CIF.
So in Singularity, all you have to do is exit the container, and then you can remove the container. Whereas it seems in Docker,
there's no daemon. There's no Singularity. There's no Singularity.
Oh, I see what you mean. Sorry, I misunderstood the question. Yeah, I see. So you're saying when you've exited the Docker container, you've still got some sort of something there in the structure, in the system. Is that what you're saying? You've still got this kind of stopped image, whereas in Singularity, when you exit, it's gone. Is that what you're saying?
I think so. I think you did answer my question anyway, but in a kind of more technical way than
right.
I was expecting.
Okay, sorry.
No, that's fine.
There's a difference in the way Docker's mapped, because Docker has this. When Docker runs, it has this daemon that controls everything. So it does the orchestration of like downloading the images, matching layers. It actually uses making sure you're not downloading layers that you've already got and all that sort of stuff, and the list images and managing the stopped containers and all that. That's all controlled by the Docker daemon, which just always runs in the background, monitoring things. Singularity is just purely file-based. There is no daemon, there's no organization, there's no management of them in the background. The cache in Singularity is just a place where things get dumped. It's literally a cache with files in. There's nothing orchestrating anything. All Singularity consists of, to a first approximation, is a special binary that raises your privileges briefly and drops them again to start the container.
Yeah. So I think sorry, go ahead, Chris.
I was going to say, so this, I was only going to half listening, but half, when you try and delete an image and it complains that the container is still running, you have to stop the container first, and then you can.
It's not still running. It's not still running. It's exited, but it knows but the container still exists. So you need to remove the container before you can delete the images associated with. That's because the Docker daemon is tracking which containers map to which images.
Oh, okay.
Yeah. So I think the difference here is that when you run Singularity, as Andy said, it's all purely file-based. If you start a Singularity container from an image, you can't edit files within that container, the files that are effectively within the image, right? It tells you it's a read-only file system or whatever. The only things you edit, unless you've specifically started it as a writable container, we won't worry about that for now. So if you just start the container normally, then you can't edit the contents of the image effectively. And so when you exit, anything that basically there's no kind of additional state that's stored, you just drop back out to your system. Whereas in Docker, when you start a container, you are getting a kind of effectively a writable layer on top of your image. So you can start changing you have the illusion of changing files you're changing stuff in the container basically. And when you stop a Docker container, you don't lose that additional layer. So I guess there's a kind of two-stage process. If you've done something in a Docker container, so say I start a Docker container and I change a configuration file in /etc or one of the directories in the system. If in Singularity I couldn't do that because it would tell me the file system is read-only. So there's no kind of additional change state. Whereas in Docker I can actually do that. What Docker is doing is it's got the image that I started off with that is unchanged, and then it's got something on top where it stores changes effectively, like a diff effectively to that image. And when I stop the Docker container, the container is still effectively in the database locally that the Docker daemon is managing, and that layer of changes is still there. So if I restart the container again, I can go back and the state will still be there. So it's kind of a sort of halfway house before you. So you have, if you remove the image, then you're removing that additional state, and then sorry, if you remove the container, you're removing the additional state. Then you can remove the image. So it's more just a kind of, yeah. I see. I think it's more a sort of multi-stage approach. But
so it's funny. What this illustrates, right, is that, in some sense, at two ends of the process, Singularity and Docker seem very, very similar, right? They both use functionality from the kernel. The Linux kernel supports containers, right? So they're both container technologies. At the other end, the commands you type look superficially similar. You know, Docker pull, Singularity pull, Docker run, Singularity run. Okay, but in between, the bits in between those two ends are fundamentally different.
Yeah.
In terms of how they work, you know, they really are. You know, and Docker, one of the reasons the Singularity looks like that is because people are used to Docker. So when you're designing the user interface to Singularity, you say, let's make it look like Docker because people are familiar with that. But they operate in completely fundamentally different ways under the hood, and it's primarily to do with the fact that Docker has a lot more management infrastructure because it wants to share layers and minimize download size and shit, and you know, all those sort of things. So it has to do additional management to launch a container because it has to know which layers are made up and which order they should be applied in. Whereas in Singularity, that just doesn't exist because it's just an image file.
So this will show my naivety with Docker. If you just take the most simple hello world image and download it from Docker and run that and just do Docker run hello world, will that still generate a separate container that is from that image? So will you still have an image and a container?
Yes.
Okay.
And each time you do issue the command Docker run hello world, you will get a new container. Right? That's true of Singularity as well, right? I mean, in terms of the image. But the difference is with Docker is those containers, unless you add the -rm option when you run it, will all sit there. Right? So if you look, let's look at this again. So let me do my screen again.
That's not the same with, so if you run a Singularity container, so if you've got a Singularity, a really, really basic Singularity container that the run servlet, postlet, whatever it's called, is just echo hello world. Every time you run Singularity run hello world, it will just print hello world to the screen, but it won't generate a new image.
No, it generates a new container, but it disappears as soon as it's finished running. There's no concept of an exited container in.
Oh, okay. Maybe I've never.
Because there's nothing to manage that. There's nothing to manage.
Okay.
That. Sorry. So
I think the point.
There you go. There's my hello world. So let me run hello world again. So now there's two hello world containers, both exited.
Oh, okay. I'd never appreciated that.
But I think the point is that there's still only one copy of the image, right? And it's just that these are effectively entries in a database, and each one has attached to it some layer that can be written to change the content of the container. So there's a sort of writable layer that's added for each of those containers. So what Docker is effectively,
I think I can do. I think I could do that.
You can, yeah, and it'll probably exit straight away again, will it? Because it's just going to run.
Yeah, okay. So because it just ran, because it's just exited again.
It just exited straight away. It ran and exited straight away.
Yeah. But if instead I did, I don't know, can you get an executable shell in the hello world?
You can if you use minus entry point and then probably bin sh. So
no, let me just do the Alpine. Let me just do Alpine instead then.
Does the Hello World one have Alpine in it? Is that what it's built on, or is it built on something else? I don't know offhand.
No, it's something even slimmer probably. So there's me in Alpine. Hello. Okay.
Yep.
Exit.
Right. So now it will have stopped, right?
Yeah. So if I do Docker container ls -all, where's the Alpine one? There it is. Here. Okay. So I could restart that. Oops. So I'm back in the shell. Let me.
Yeah. That's what I was going to say. If you if you add a file or change
Okay. So it was just a minute. So I've added t.dat here. I'm going out of the container again. So that one is exited again, right?
Yeah.
But if I go Docker and restart it, you should see it's running, or let's say it's up 1 second rather than exited. Okay. And then if I attach back to it, that file I touched before is still there, even though the container exited. And that's what Jeremy was saying, right? There's a layer there that I can do things to and persists. Which doesn't exist. That doesn't exist for Singularity.
Yeah.
Because of the way it's managed.
I've been in the Singularity ecosystem too long.
Okay, I need to go and get. I need to take the dog around the field and go and get some lunch.
Yeah, sorry.
No, but it's useful. But it is. This is a function of the fact that at two ends they're similar, right? And particularly in the interface end with the people interact with, they look very, very similar. But fundamentally, they operate in fundamentally different ways. Singularity and Docker, apart from the bit at the end, which is just the kernel support for containers. Okay, the rest of it is completely different.
Yeah, thank you. That was useful for me, at least.
No, it is useful. It is useful because it's not obvious, right? If you're just interacting with them on a day-to-day basis, it is just not obvious that there's all this stuff behind Docker extra going on.
Yeah.
Right, I'll see it at 1:30 anyway.
Yeah, I'll let you take your dog out.
Yeah. Okay.
Okay.
In a bit.
Cool. See you later.
Cheers.